Okay, so yeah, I think lab 2 is relatively straightforward. So basically, I think maybe next week I'll upload lab 3, so which is much more interesting and challenging. So if you finish lab 2 early, so you can start lab 3. Yeah, lab 2 is very straightforward. Lab 3, for lab 3, you're gonna use the software-defined radio dongle that we introduced in our first class, right? Make sure that you have it before next week, okay? All right, so any questions? Okay, so let's give a brief review of our last lecture. So in the last lecture, we talked about energy spectral density, okay? And and here is how we derive it. So basically, we introduce you LTS system, and this is the unit impulse response of the system in the frequency domain. So right, so with that is a bandpass filter, right? Only certain frequency can be passed by using this filter, and so basically, after some manipulation, so we can compute. So the energy of the output signal is given by this kind of formula, right? And here we can see that we didn't specify which frequency range that we're picking, right? So for any frequency range from FL to FH, from F low to F high, so this is how we compute the energy, right? So basically we say, okay, so if we can compute the energy in this way, so basically this integrand can be understood as some kind of density, right? And that's our definition for the energy density. And since it's in the frequency domain, so we call that energy spectral density, right? Spectral basically means the frequency domain, all right? And and we define psi g, right, as GF of the value square. So that is our density, energy spectral density. Okay, and we give a particular example of how we compute this ESD, right? You can see the lecture notes for the details. All right, and then we'll give another example. So basically, let's consider a modulated signal, which is given by that, right? So basically, this is what you have in your lab 2, right? So just have that. So we call that a modulated signal, right? And the reason we call that modulated signal or modulation is that in the frequency domain, so what we have is as follows, right? So we have two shifted versions of the original signal, right? One is on the right, and the other one is on the left, right? And for this kind of signal, let's compute the energy spectral density. So basically, this is how we compute it, right? So we use the definition of norm, right? We write that as this guy multiply this guy conjugate, right? And then after some manipulation, we find that, okay, so this is something we have, but for this guy, so that becomes 0, right? Because we use GF minus F naught times GF plus F naught, right? So there's no overlapping between this guy and that guy, so the multiplication of this is 0, all right? And this is what we got, right? So this is very nice, right? Because so this is our signal, right? Its energy spectral density is nothing but each of the items squared. That's it, right? We don't have any cross term. Okay, that's very nice. So this is how we compute the energy spectral density of a modulated signal. And then, so we introduce the concept of autocorrelation function. So basically, autocorrelation function means that a function multiply with its own, itself, right? But it's a shifted version of itself, right? And then we do the integral, right? In other words, so we compute the norm between a signal and a delayed version of its signal, right? So, and this is called autocorrelation function. And clearly, so because this is a function of tau, and the result is function of tau, okay? And the reason we have it, or the cool thing of this guy is that, so before we talk about the cool thing of it, there are like two properties we have to introduce. So one property is that this guy is an even function, right? So psi g tau equals to psi g minus tau. And the other interesting property is that so we can write it as a convolution of g of t and g tilde of t, where g tilde of t is defined by the negative t, g of negative t, right? since we can write the autocorrelation as a convolution between these two signals, then it means that in the frequency domain, it's a multiplication between this guy and that guy, right? And this is what we do here. So in the frequency domain, if we do, there should be a G here. So if we do a Fourier transform of the autocorrelation function, and then we can see, so convolution becomes a multiplication of this and that, right? And this is GF times the GF conjugate, right? Because so G, this guy equals to G negative T, right? And then this guy will become this, right? What's that? Right? That is the energy spectral density, okay? So this formula basically tells you that the energy spectral density is nothing but the Fourier transform of the autocorrelation function, so which is very nice. Okay, so this basically means that if computing this is hard, we can compute the autocorrelation function, and then we do a Fourier transform, and then we get it. Okay, so sometimes computing autocorrelation function is a much easier job than comparing this. Okay, and I think that is where we finished in the last lecture. Any questions? All right, so today it's our lecture number 11. So we're going to talk about something very similar to energy spectral density. So it's called power spectral density. Right, so probably we're gonna just talk about this in today's lecture, but just give you a heads up. So after that, we're going to talk about modulation. So basically, we'll start with the form that you have seen so many times, right? G of t times cosine, right? That's called amplitude modulation, but there are some other form of modulation. So basically, we're gonna go over each of them in very detail. Okay, and so this is in our chapter 4 in the book. Okay, we're gonna probably cover that in the next lecture, and that's your lab 2 is also about modulation. Okay. So yeah, let's see. Yeah, power spectral density is also called PSD, right? Okay, first let's see the concept of power spectral density and autocorrelation function. Right, so now first let's remember how we compute the power of a power signal, right? So first of all, consider G of t, and that is a power signal. In our class, when we mention power signal, so that's normally a periodic signal, okay? So this is what we, how we think about power signal. And who can tell me what is the definition of power of G of t? Yes.
Limit as t goes to infinity.
Very good.
1 over t.
Uh huh.
And then integral from negative t to t of g of t squared.
dt, right? Almost. Yeah, we just put a half here to make the length of that equals to t. Very good. Okay, and so this is a general definition for the power of a power signal, right? And if it's periodic, then we can put here as t naught, right? The fundamental period, and then we can remove this limit. Okay, very good. So this is a general definition of the power. And now let's see how we can compute the power in a different way. Okay, so basically our manipulation is like this. So we define a new function, which is called g capital T of t. Right? Clearly, if we write t here, it means that g is related to this capital T. So this capital T is this capital T. Okay. So basically, g t of t is nothing but it equals to gt right? When t is less than or equal to capital T divided by 2, okay, and 0 otherwise, right? So we just pick, the middle part of GT, so that's defined as GT, G capital T, okay? And given this, so we can rewrite the definition of PG in terms of this guy, okay? Let's see how we can do that. PG, let's write it down. So basically, we still have T goes to infinity, and then 1 over T, okay? So now, let's replace this guy by this guy, okay? So basically, we do this. Can I do that? Or if we do that, so what should be the integral limit? Would that still be this? Sure, of course, right? That should work. But can we write something different? Right? Let's say, so basically, in the limit, t is a constant, right? So t is now infinity, right? We compute this, and then we let it go to infinity, right? So for this guy, and for this, so this is kind of, we cut it at t, right? Therefore, this guy becomes a energy signal, right? So basically, the integral limit, we can write this as this, right? Because everything else is 0, okay? The integral still, from here to here, there's no problem, but we're just including everything here because, so GT, so we cut it, we truncate it. Yeah, that clear, this step? Yeah, that's the most important step, right? So if we understand this, then, for energy signal, we have learned a lot, right? So then this is nothing but the energy of G capital T, right? So since we have learned what is energy spectral density, so can we write this as the energy spectral density, right? Can I write it? So in terms of capital GT, F, right, from what we learned in the last lecture, so this equals to what? Remember, so this guy is energy spectral density, right? And then if you do an integral of it over F, then it'll give you the energy, right? So this and that are equal, right? So this is what we learned from the last lecture, right? So compute energy in the time domain will be equal to computing energy in the frequency domain in this case. Is that clear? This step? Yeah.
Yeah, that's just Parseval's theorem?
Yeah, exactly. It's Parseval's theorem. Very nice. And OK, so next step is that, so let's assume that we have a very nice function, so this is a limit, and this integral can be exchanged, right? So then we can just have this integral out, and then inside, we let t goes to infinity. Okay, and then we have G capital T of F square T dt, df, sorry. Okay. Very nice. So why we want this form? It's because we want to get this guy, right? So basically, the power of the signal, P of PG, will equals to the integral here, right, over F, and we have something inside, right? And this integrand must be some kind of density, right? Integral over the density, and then we can get the power. Okay, so this guy is called what? The power spectral density. Right, the idea is the same as when we derive the energy spectral density, right? Something inside the integral. So this is called power spectral density. Let's make it official, so we have a definition. power spectral density. Okay, so basically for a power signal, G of t, right? And then the power spectral density is given by, so we denote that as SGF. So that is the limit t goes to infinity and the G capital T F square over T, right? So that's the definition of the power spectral density. Okay. And clearly from here we can see the power will equals to this, right? We do integral over the power spectral density, and then we can get the power of the signal, right? And if, let's say, GT is real, yeah, similar to the case of the energy spectral density, so the power will equals to 2 times from 0 to infinity of this guy. Okay, so this is similar to what we have for the energy spectral density. All right, any questions so far? Okay, and of course, if we want to compute a power in some specific band, right? Let's say the power in the band from FL to FH, from low to high, as what we did in the energy spectrum density. So this power equals to FL to FH, and then we have SGF dF, right? This is how we compute the power in a specific band. Okay, yeah, that's the definition of the power spectral density, which is very similar to what we have for the energy spectrum density, right? So this is maybe a little bit weird, right? Because power is already some form of density, right? It's the energy per unit time. But then for the power spectral density, we sort of normalize it again over the frequency domain. Okay, so that's somehow the meaning of it. Okay. So, yeah, and this is definition, right? So the next thing we want to consider is how we compute it, right? How can we compute it? Right? So is that easy to compute using this? Right? We don't know, right? But it's somehow complicated, right? Because we need to compute this guy from GT, right? The compute is Fourier transform, and then divide by t and let t go to infinity, right? So we have a number of steps to follow to compute this guy, right? So in practice, computing this guy using this formula is very hard in general. Okay, you can try it. Sometimes it can be manageable, but normally it is not that easy to use this formula directly to compute the power spectral density. Okay, so then what should I do? Let's say using this approach is not easy to compute it. So can you think another way to compute it? Right, remember, so the power spectral density is very similar. The concept is very similar to the energy spectral density. Right, for the energy spectrum density, computing that from the frequency domain might be manageable, right? But is there another way to compute it? Yes.
Can't we use the autocorrelation?
Very good, right? For the energy spectral density, we can compute that directly using definition, or we could compute the autocorrelation function first, and then using Fourier transform to compute that, right? Can we do something similar here? Right, so this is the definition of the power spectral density. Can we compute the autocorrelation, or define kind of autocorrelation function and then compute that and do the Fourier transform to get it, right? So that's another route, okay? So let's see whether that is possible or not, right? So that's basically what we're going to do next. We're going to see how we can compute the power spectral density. Calculating PSD. So basically, the idea is exactly the same as before, right? Let's write it down. So similar with the energy spectral density, right? So we can calculate PSD as the Fourier transform of the autocorrelation function. Autocorrelation function. Okay, very good. Okay, so now we need to define what is the autocorrelation function, right? So definition. Autocorrelation function okay, this is for power signal. Okay, who still remember the definition of the autocorrelation function for energy signal? Right, the psi g of tau. Yeah, what does that equal to? Yeah.
It's like the inner product of g of t with g of t minus tau.
Very good. Right, if you write it down, if you write it out, it will be equals to this, right? Very good. And for power signal, can you imagine something similar to this form? Right, the idea has to be very similar, right? So can you take a guess? I see, yeah, I will write this as RG tau. So that's the definition. That's the notation for the autocorrelation function for power signal. So take a guess, right? So can you tell me what should be the definition of it? Yeah, it should. Yeah.
The same thing because
Same thing.
replace r with g.
Exactly same thing.
With r.
Exact same thing. Yeah, see whether there's a problem or not, right? Imagine, so now G of t is a power signal. Yeah, it's not energy, right? So first, we need to let G of t be a power signal, right? So that's not an energy signal, right? If it's a power signal, if we do that and then do the integral, probably it will become infinity, right? Because the signal is everywhere, right?
So just do t to, or negative t over 2 to.
Very good, right? That's the way we solve the problem, right? So we compute and time average, right? So let G be a power signal, then the autocorrelation function. Is given by the follows, right? It's very similar to that, but the difference is that, so instead of doing the integral from negative infinity to plus infinity, so we do that as the trick we used before, right? From negative t half to t half, and then we normalize it by t, and then we let t goes to infinity, right? This is how we define it, right? Does that make sense? Yeah, so yeah. That's how we do that. And then we're not going to show it. So the math is almost exactly the same as before. Okay, I believe you can show that on your own, right? The same thing here. So we do a convolution, right, between the two guys. So basically, this is a fact, right? So GF is nothing but the Fourier transform of RG tau. right? So that's a fact. Okay, and actually it's a name of a famous theorem. So this is called Wiener Hintschen theorem. Okay, Wiener-Hintschen theorem. Yeah, and this has been very widely used in wireless communication. Okay, especially for random signals. Okay, because in practice, almost all the signals are random. So basically, we can use this relationship to compute the power spectral density. Okay, so that's extremely important and popular. So any questions so far? Okay, if no, so now I'll demonstrate to you how we can really compute it from here to here, right? So why it is not so hard to do. Okay, let's see an example. Okay, as we said before, so probably the most important power signal that we care about is what? The power signal, right? Sorry, the periodic signal, right? So let's consider periodic signals. Okay, so now let's consider g of t. It's a periodic signal. And with fundamental period of t naught. Okay, then let's see what does the autocorrelation function look like. Okay, so we just computed from scratch from the definition. Let's see how we can do that. So now we cannot write anything, just get rid of the limit and then put the t naught there, right? So we don't know whether that's true or not, right? We have to derive it from scratch. Let's see how we can do that. So we write down the definition. Okay, so gt minus tau dt. Okay, so now let's do some manipulation here. Okay, so yeah, so this is the first step, right? So that's the definition. And then how should we get something meaningful, right? Because compared to the just power signal, so now we know g of t is a periodic signal, okay? If it's periodic, what should I do? Or what we learned about a periodic signal? Because now we're thinking something related to the frequency domain, right? So for a periodic signal, can we think anything about the frequency domain? So in other words, can we write something here, right? So we want to replace g by something else to make it meaningful, right? So what can we write here for a periodic signal? Yeah.
Maybe we could add the subscript of t so that the bounds are changed to negative infinity to positive infinity because it's truncated.
Mm-hmm.
So we could have we can use the phi equation.
Oh, interesting.
Because it would truncate the integral from half integrated to
Yeah. Yeah, I think if I give you a specific form of g, yeah, maybe I think you can do something like that, right? But now we consider general g of t, right? Even if we do that, and then we are going to write this as a function of g capital T, right? That is not what we want, right? So the reason is that if we write something like that, and then we cannot go back to the original definition, right, of the power spectral density. Right? Remember, the original definition of power spectral density is given by this capital G, capital T, right? So yeah, we may know something exactly like that. So can we do something some other stuff? Yeah, for periodic signal, so what can we do? So we can do the Fourier what? Series, right? So how about we plug in the Fourier series for this guy or this guy, and then take a look, see whether we can get anything meaningful. Does that make sense? Right, so basically what we're going to do is that we're going to use the Fourier series to replace one of this guy, okay? And as you can see later, so this is the trick. Maybe we have done this a few times already, right? So this is a trick normally we do, okay? When we want to manipulate something, we replace its Fourier series or Fourier transform, the inverse Fourier transform, for example, right? And then we can see where we can get, right? So basically, yeah, this is what we're going to do, right? Let's keep everything stay the same, right? And then what we're going to do is that we're going to replace this guy by its Fourier series. Let's see what we can get. Okay, so for Fourier series, yeah, let's write it as the dummy variable. We write that as m, okay? And this is our Fourier series coefficient. And then it's E what? J 2 pi mf naught. And then we'll have t minus tau, right, conjugate dt. Okay, so this is what we got. Okay, and so the other trick that we're going to do is that because g of t is periodic, right? So we can break this integral limit into period, right? Fundamental period, right? So let's see. Basically, what we're going to do is like this. So basically, we're going to replace capital T by 2n t naught, right? And then we replace this integral by a summation of a bunch of small integrals, right? So basically here we use another dummy variable, k, from minus n to n minus 1. And here we have k t naught to k plus 1 t naught. Okay, and clearly here we need to let n go to infinity. Okay, and then we have gt. Does that make sense? So basically, we break this big integral into a bunch of small integrals, and the length of each small integral is t naught, and then we'll add them up together. Right? The reason we have from minus n to n minus 1 is to make sure that overall we have 2n item, not 2n plus 1. Yeah, if you make it from minus n to n, then we need to make here as 2n plus 1, so which is also okay. Does that make sense? Right, and then, so we have this guy. Yeah, let's copy it. Or, we can put this conjugate inside, right? So let's put the conjugate inside. So we have a summation over m as n conjugate e minus j 2 pi mf naught t minus tau dt, sorry. Okay, so this is what we got. Pretty messy, right? And next, let's see what we're going to do. So what should I do? Normally, if I have this kind of form, yeah, normally we will, so we have this kind of situation before. So basically, we can see, inside this integral, we have a bunch of items that is not related to t. So we can take those items out and see what we get. Does that make sense? Right. So this is, this is what we're gonna see whether we can get anything that makes sense, right? So 1 over 2n t naught, and then we're gonna write this guy out and then see what we get. So basically, this summation over n, so that has nothing to do with the t, right? So we can take that out as n, And here, so we have an item related to tau. So that's not a function of t, right? We can take that out. So we have a minus here, and we have a minus here. Then it's a plus j 2 pi m f naught tau. Okay, very good. And then we can write down the integral, right? So basically, now we have this summation, k, from minus n to n minus 1, k t naught, k plus 1, t naught, and g of t. And so what we left here is this t term, right? So that's e minus j 2 pi m naught, m f naught. Yeah, a bit complicated here. Just follow, hopefully, and dt. Yeah, did I miss any term? Yeah, should be like this. Should be like this, right? Do you agree? Sort of? Yeah. Okay, so now let's see. Did you see anything from here? Anything interesting? Right, how about this? Right, what is it? What's that? So GT is periodic signal. So that's it's a Fourier transform, but here is the way to compute the Fourier series coefficients, right? I mean, yeah, it has the same position as a Fourier transform, okay? But do we miss anything? Because g of t is periodic, so when we compute that, so we should have a normalization factor 1 over t naught, right? Do you remember it? And we have it here, right? So yeah, we just move this guy to here, and then so this will give us the Fourier coefficients, right? Which is Sm. Yeah, does that make sense? Yeah, kind of messy, but we're arriving something really nice. Okay, so now we replace the entire thing by Sm, and then so let's write down the whole thing. See what we left. We have 1 over 2n here left, and the middle guy is Sm e j 2 pi m f naught t, and then we have a summation over k, and this. Okay, and you know, this is not a function of k, right? So summation over k basically means we add this number of times, right? Therefore, we can replace this by the number of items here, so that's 2 times n, right? Yeah, because the summation, so this is a summation over k, but inside is not a function of k anymore, right? K appear here, right? So it doesn't matter anymore. Okay, and this 2n and this 2n will be canceled, and this limit will not matter anymore because so everything inside is not a function of n, right? Yeah, I think I missed a conjugate somewhere. So here should be a conjugate, sorry. Right, because we have a conjugate here. Okay. All right, so now we have something really nice, right? So this multiply that is nothing but Sm norm square, and then ej 2 pi m t. Okay, so that's, oh, it should be, sorry, it should be tau, not t, right? Replace. Right, because we have a tau here. Okay, this is what we got. Okay, let's summarize. So the autocorrelation function for periodic signal has something very nice, right? Remember, so this is for general autocorrelation signal, right? Right? Okay, so given this form, so can you tell me what is the power spectral density? So which is a Fourier transform of this guy? Right, so basically now, so it's a Fourier transform of this guy, right? Because of the linearity property of the Fourier transform, we just move this f inside, and then we can have this Fourier transform of this, right? And then what is the Fourier transform of this? So what's the Fourier transform of a complex exponential? Yeah.
The delta signal at f naught.
At what?
At the frequency that's at, I think it's f naught.
Yeah, m times f naught, almost, right? Yeah, so basically, so this is a complex exponential. Its Fourier transform is a delta signal like this, right? Here's plus, I think here's minus. Yeah, okay, great. And then, so we can write, so eventually, so the power spectral density of a power, yeah, let's write the whole thing. The power spectral density of a periodic signal is nothing but this guy. Right? Which sort of makes sense, right? Because it's a periodic signal, and then we cannot compute the Fourier transform, right? It should be represented by a summation of a bunch of delta signal. And the nice thing here is that the coefficient in front of each delta signal is specified by the norm square of the norm of the Fourier coefficients, which cannot make sense, right? If it's not, if it's not power spectral density, it will be just Sm times delta, right? So that's the Fourier transform of periodic signal, right? But now, the power spectral density is just equals to that thing squared, right? Kind of. Yeah, does that make sense? Okay, so if that makes sense, let's see a very simple example here. So basically, yeah, maybe let's just write something here. So we're going to see the example of the square waveform again. Right, let's see what the power spectral density look like. Okay, so we consider a square waveform like this. It's a unipolar square waveform. So now the length, we consider that is, let's say, TB over 4 minus TB over 4. Okay, and the period of this is TB, something like that. Yeah, here's minus TB. Okay, and if I want to write it down, so we can write that as G sum over n, G t minus n, TB. And for each of GT, so that equals to this guy. So now the width, the total width here is TB over 2, right? So then we have to write T over TB over 2, right? So that's our signal. If we consider a signal like that, so let's compute this guy, right? Okay? Yeah, now we need to remember everything we have learned so far, okay? So how can we compute the Fourier series coefficient? Remember? So one way to compute it easily is to use a Fourier transform of a single item here, right? So what's the Fourier transform of this guy? in the middle, GF, right? That should be a sync signal, right? So yeah, let's see whether you can remember everything or not. So normally that is equal to tau sync pi f tau, right? So this is what we got before. Now tau is defined by the width of it, right? So now tau is nothing but TB over 2, right? If we plug that in, so we can get the Fourier transform of this guy, right? But now let's remember, so here, yeah, Sn or Sm, so I just use notation n here. So Sn is nothing but 1 over what? Tb of G n over Tb, right? If we plug everything in, so that is what we got, right? Because Tb is the period of it, right? Okay, so now we need to plug things in here, right? So basically, so for this guy, I mean, yeah, notation is kind of, I use G prime to denote. Yeah, that's right. Yeah, because I say GF is the Fourier transform of this guy, right? So, and I think it should be fine. So basically, that's the formula we need to use, right? Now we need to plug in specific G, right? So which is this guy, replace tau by TB over 2, right? So let's do that. So 1 over TB, and then tau equals to TB over 2, right? So TB over 2, and the G, oh, not G, the sync, pi n over TB, because that is, we replace this guy by n times f naught, right? Like this, n over TB, and times TB over 2, that's the value of tau. Okay, and now let's do some simplification. So this TB and this TB canceled. We'll have 1 over 2 sync. And here, this TB and this TB canceled. We'll have n pi over 2, right? So that's the Fourier coefficient. That's the Fourier series coefficient, right? And now we need to, because if we compute that, we need to compute the square of it, right? So let's compute the square of it. So that is 1 over 2 sync n pi over 2 squared. Okay, so now let's write it out a little bit, right? So this absolute value doesn't matter here much, right? Because it's a real signal. And then the sync is defined as sine n pi over 2 divided by n pi over 2, okay? And squared, okay, squared. And we have 1 over 4 here, and we have 1 over 4 here because we have 2 squared, right? So then basically what left is something pretty nice, n squared pi squared, right? So that's what we have. Okay. Yeah, and actually we can write down this function pretty nicely, right? So here, when n is 0, we can compute it using L'Hopital's law. So that is 1 over 4, right? And when n is odd, so that is this guy, n squared pi squared. Otherwise, it will be 0, okay? 0 otherwise. Okay, and then, so if I want to draw it, it will look like this. So the envelope would be still a sync, right? We draw Sn, yeah. We should not have this negative side, right? We want to draw the square of Sn, so that will be like this. Right, and basically all the value of Sn would be this value, right? This is 1 over 4, and then we'll have this value. That is 1 over pi over 2, and then we'll have 0. And similarly, so we have 0, 1, 1. So here should be 0, and so on, and so on, right? Yeah, basically all the value of this guy will be taken here, and we'll have 0 here, 0 here, and so on. right? And that's it, right? If we know that, then we can write down the power spectral density. Okay, so this is how we compute the power spectral density, right? So if I'm going so fast, right, just go over this again after the lecture, and you'll see. Okay, and I have one more example written down here to compute the power spectral density of a random signal. So yeah, that is a very lengthy. So I'll upload it. You can look at that offline. So we're not going to go over that in the class. So it'll take a whole class to go over it. It's pretty complicated. But you'll see the idea, right? It's not so different from here. Okay, so I think that's all for today. So next lecture, we're going to cover modulation.